So in molecular orbital theory, according to this theory, the electrons of the molecule are filled in molecular orbitals, just like electrons of an atom are filled in atomic orbitals. Atomic orbitals are monocentric and molecular orbitals are polycentric. Okay, and electrons are filled as per above principle, Hund's rule and Pauli's exclusion principle. All the three principles are used in molecular orbital as well. Now up to nitrogen, energy of the molecular orbital is sigma 1s, sigma star 1s. Sigma 1s means bonding molecular orbital, anti-bonding molecular orbital. Sigma 2s, sigma star 2s, pi 2px and pi 2py. They have same energy, and then sigma 2pz, after that pi star 2px, pi star 2py, sigma star 2pz. These are the molecular orbitals as per above principle in the order of increasing energies. Lowest energy orbital is filled first, and then accordingly they are filled. And for O2, F2 and Na2, sigma 1s and sigma star 1s, we can write it as Kk because they are inner orbitals. Then sigma 2s, sigma star 2s, sigma 2pz, pi 2px, pi 2py, pi star 2px, pi star 2py, and then sigma star 2pz. Now question arises, why here up to nitrogen pi 2px and pi 2py are of lower energy than that of sigma 2pz, and for O2, F2 and Na2, sigma 2pz is of lower energy than that of pi 2px and pi 2py. Rest is same. So why is it so? Difference is because of the interaction. Actually 2s orbital and 2px, 2py and 2pz, out of 2px, 2py and 2pz, say 2pz from sigma bond and 2px, 2py from pi bond, because Z is taken as internuclear axis. What is internuclear axis? When two atoms combine, two atomic orbitals combine, then the line which passes through the nuclei, that is called internuclear axis. So internuclear axis is taken as Z. That's why Z forms sigma bond and X and Y that form pi bonds. First. Second, when 2s orbital overlap with 2px or 2py, then it is a zero overlap for 2px as well as 2py. Means 2s orbital cannot interact with 2px and 2py. There is zero overlap between 2s and 2px or 2s and 2py. That means there is no interaction between 2s and 2px, 2s and 2py. But when we talk about, this is 2px, same in the case with 2py. If we use 2s and 2pz, see, this is z axis and this is internuclear axis. So 2s can effectively interact or can effectively overlap with 2pz. And when the overlap takes place, when their energy difference is less. There is slight energy difference or no energy difference. Then 2s can interact with 2pz. They can interact, but condition is their energy should be comparable. Energy should be comparable. They are symmetrical, but their energy should be comparable. So up to nitrogen, energy difference between 2s and 2p is low. Up to nitrogen, energy difference between 2s and 2p is low. That's why 2s can interact with 2p. But 2s and 2p, which orbital of 2p can interact? Only 2pz. 2px and 2py cannot interact. So 2s and 2pz can overlap, or we can say can interact up to nitrogen because their energy difference is less. Why is it so? Because when nuclear charge increases, your 2s come closer to the nucleus. 2p is not attracted as much as 2s. 2s is attracted more toward the nucleus than 2p. Clear? S, P, D, F. S is closest, then P, then D, then F. But as nuclear charge increases, the energy difference between S and P goes on increasing. So up to nitrogen, nuclear charge is not large enough so that 2s cannot interact with 2p. But when there is a term of oxygen, then fluorine, then neon, then there is large energy gap between 2s and 2p. Therefore 2s cannot interact with 2p. Right? But when they interact up to nitrogen, then one has lower energy, other has higher energy. So obviously 2s is of lower energy, 2pz is of higher energy. That's why that gap increases when they interact. That's why sigma 2pz crosses pi 2px and pi 2py because of interaction. That means in this sigma 2pz there is sp character. There is sp character. Here also there is sp character. Normally we will not show it, but keep in mind up to nitrogen 2s is not pure 2s. It has some p character. 2pz is not simply p, pure p, it has some s character. And because of that sp character, sigma 2pz is of higher energy and sigma 2s is of lower energy. Right? Now, when we come to O2, oxygen, fluorine and neon, there is a large energy gap. So, there is no interaction between 2s and 2pz. So, normal order follows. You know, sigma bond is stronger than pi bond. That's why sigma bond is of lower energy than pi. Up to this point, pi bond is of lower energy than sigma. Why is it so? Because of this sp character. Because of the interaction of 2s with 2pz. Keep in mind this. Right? Now, in case of H2 molecule, you know, hydrogen has one electron. So H2 has two electrons. So fill in. Only there is sigma 1s 2, sigma star 1s 0. That means if we draw molecular orbital energy level diagram, this is 1s for hydrogen atoms. Now H2 molecule, this is sigma 1s, sigma star 1s, because when 1s overlap with each other, bonding has lower energy than pure atomic orbitals, anti-bonding has higher energy than pure. So this is 1s 1s1, 1s1, and this becomes 1s2. Sigma 1s2. Accordingly, we can calculate bond order. What is bond order? Number of bonds between two atoms. So it is bonding electron minus anti-bonding divided by 2. So it is 2 minus 0, because in anti-bonding there is no electron. So it becomes, so there is one bond between hydrogen atoms. What about magnetic vector? So H2 is paramagnetic or diamagnetic? Diamagnetic. Because they are diamagnetic because of paired electrons. And what is diamagnetic substances? Which are weakly repelled by the magnetic field. Diamagnetic means they are weakly repelled by the magnetic field. And if they have unpaired electrons, then it is paramagnetic. And paramagnetic means they are weakly attracted by magnetic field. Diamagnetic substances are weakly repelled by magnetic field. Paramagnetic substances are weakly attracted by the magnetic field. Here all electrons are paired. In this case, all electrons are unpaired. Not all means at least one unpaired electron should be there. H2 plus. So in H2 plus, there is only one electron. So if there is only one electron, it becomes sigma 1s1. So that is H and H plus. There is only one electron. Sigma 1s1. So bond order is 1 minus 0. That means bond order is 0.5. Then H2 negative. That is sigma. It has now 3 electrons. 2 electrons from H2 and 1 negative. So sigma 1s2, sigma star 1s1. That is H and H negative. So total 3 electrons. 2 are in bonding and 1 is in anti-bonding. So what is bond order now? 2 minus 1. That means 1. So now, if we compare bond order of H2 is 1, or bond order of H2 plus and H2 negative is same. Now, what about stability of these species? What is the order of stability? Normally, what we do, we write stability is proportional to bond order and inversely proportional to bond length. Stability is proportional to bond order and inversely proportional to bond length. But in this case, you know, H2 plus and H2 negative both have same bond order, but keep in mind H2 plus is more stable than H2 negative. Why is it so? Because as per one statement, bonding is less bonding, anti-bonding is more anti-bonding. So what it means, you know, when we write H2 plus, we remove electron from bonding. So it decreases the stability. It decreases the stability. But what I said, bonding is less bonding. That means decrease in stability is less. But anti-bonding is more anti-bonding. That means that when we add electron in anti-bonding, its stability increases more. Its stability decreases more than when we remove electron from bonding. When we add electron in anti-bonding, that decreases the stability more than when we remove the electron from bonding. See, H2 plus and H2 negative both are unstable or both are less stable than H2. But its stability decreases because we remove electron from bonding molecule. Its stability decreases because we add electron in anti-bonding molecule. So when we add electron in anti-bonding, decrease in stability is more than when we remove electron from bonding. Right? That's why H2 plus is more stable than H2 negative, though they have same bond order. Though their bond order is same, but H2 plus is more stable than H2 minus. Okay? Molecular orbital energy level diagram. Helium 2. For helium, one S and sigma 1s, sigma star 1s. For helium, it is 1s to 1s 2. Sigma 1s, because total 4 electrons, so sigma 1s to sigma star 1s 2. It is sigma 1s to sigma star 1s 2. So, what is bond order? Bonding minus anti-bonding is 0. It means there is no bond between helium atoms. That's why helium 2 does not exist. अगर question आए कि why helium 2 does not exist, so as per molecular orbital theory, bond order of helium 2 is 0. That means there is no bond between helium atoms. That's why helium 2 does not exist. Okay. So let's draw molecular orbital energy level diagram for second period elements. Lithium, beryllium, boron, carbon, nitrogen. Up to nitrogen, and then for oxygen, fluorine and neon. 2s. Because now 1s in inner orbital, 2s, this is one atom, this is other atom. And for molecule, sigma 2s and 2s form sigma 2s and sigma star 2s. 2s overlap to give sigma 2s is of lower energy than pure atomic orbitals. Sigma star 2s is of higher energy than that of atomic orbitals. Then come to 2p. P, 2px, 2py, 2pz. Same 2px, 2py and 2pz for atoms. Now when they overlap, 2px overlap with 2px, give pi 2px and pi star 2px, 2py overlap with 2py, to give pi 2py and pi star 2py, 2pz overlap with 2pz, to give sigma 2pz and sigma star 2pz. So up to N2, which has lower energy, pi 2px and pi 2py. So it is of lower energy. And then sigma 2p bonding orbitals have lower energy than at pure, and then pi star to px, pi star to py, and sigma star to pz. Then O2, F2 and N2. For O2, F2 and N2, US, sigma 2s, sigma star 2s, now in this case sigma 2pz is of lower energy, pi 2px, pi 2py, pi star 2px, pi star 2py, sigma star 2p. Px, 2py, 2pz, 2px, 2py. Now say lithium 2. How many electrons are there? Lithium has 3 electrons, so total 6. 6 means sigma 1s2, sigma star 1s2, and then sigma 2s2. So what is bond order? Bond order is 4 minus 2 by that is 1. Bond order is 1. So see, it is 1s2, 2s1. 1s2, 2s1. So 2s1, 2s1. So it is sigma 2s2. So that means there is one sigma bond, because sigma 1s, sigma star 1s cancel out each other. So there is one sigma bond between 2s and 2s. Right? Now come to, and it is diamagnetic. What about the helium? 1s2, 2s2. Like this. So that means it becomes sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2. So it becomes 4 minus 4, that is 0. That means there is no bond between beryllium atoms. So beryllium 2 does not exist. Boron. So boron is 1s2, 2s2, 2p1. So it is 2s2 and 2p 1 for boron. So that means it becomes like this because they are of same energy. Pi 2px and pi 2py have same energy. That's why both have one electron as per Hund's rule. So B2 is sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, and pi 2px, pi 2py 1 1. So what is bond order? One is 2 plus 2 plus 2. 6 minus 4, that means 1. But this one bond order is sigma bond or pi bond? It is a pi bond, keep in mind. Otherwise, you know, whenever single bond is always sigma bond. As per our, when we study, we write sigma bond can exist independently, but pi bond is always accompanied with sigma bond, right? But in case of B2, one bond is formed and that is pi bond. One bond is formed and that is a pi bond. And at the same time, this pi bond, you know, pi 2px has one electron corresponding pi star 2px. Pi 2px has one electron, pi star 2px has 0 electron. So with respect to 2px, there is half bond order. With respect to 2px, there is half bond order. With respect to 2py, again half bond order. There are two half pi bonds. That means this one is formed by half plus half. This pi bond is formed by half plus half. Keep in mind. Same is the case with C2. When we talk about carbon, in carbon there is 2s2, 2p2, 1s2, 2s2, 2p2. So this is like this, and it becomes clear. D2 is paramagnetic, but C2 is diamagnetic. C2 is diamagnetic, and now bond order is 2. Bond order is 2. 1 plus 1. Pi 2ps, pi star 2px. 2 minus 0. Pi 2py minus pi star 2py. So 2px form one pi bond. 2py forms another pi bond. So total bond order is 2, and both the bonds are pi bonds. Okay, C2 cannot exist in solid state. It exists only in gaseous state. It exists only in gaseous state. Okay. N2. It is 1s2, 2s2, 2p3. It is sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi 2px, pi 2py, and then sigma 2pz2. So in this case, 10 minus 4, so it is one sigma bond, 2 pi bonds. One sigma bond, 2 pi bonds, and it is diamagnetic. C2 and 2 both are diamagnetic. B2 is paramagnetic because B2 has 2 unpaired electrons. Now come to O2. In case of O2, diagram changes. What is the change? Sigma 2pz is of lower energy than pi 2px and pi 2py. So draw for O2. For O2, for sigma 1s and sigma star 1s, write KT. Then it is 2s2 and 2p 4 2s2 2p4. So total it is sigma 2s2 sigma star 2s2 sigma 2pz2 total 4 plus 4 8. So 1 2 3 4 5 6 7 and 8 mean now there are unpaired electrons. So O2 is paramagnetic and it is sigma 2s2 sigma star 2s2 sigma 2pz2 pi 2px pi 2py 2 pi star 2px pi star 2py 1 1, right? So in this way it is paramagnetic and bond order comes out to be 2 plus 2. There is no need to count KT. So 2 plus 2 4 6 8 8 minus 4. So bond order is 2 and it is paramagnetic. In case of F2 this 2s2 and 2p 5. So it becomes pi star 2px2 pi star 2py2. It is 1 and it becomes diamagnetic. F2 is diamagnetic. What about neon 2? Neon 2 in this case it becomes sigma star 2pz2. So bond order comes out to be 0. Again neon 2 does not exist. So that is all about MOT for homo-diatomic molecules. We will continue with heterodiatomic molecules next time. For homo-diatomic like O2, O2 positive, O2 negative and O2 2 negative. You can calculate just by looking at the configuration. For O2, there is pi star 2px1, pi star 2py1. If electron is added in antibonding, bond order is decreased by half. If electron is removed from antibonding, bond order is increased by half. If we add electron bonding, bond order is increased by half. If we remove electron from bonding, bond order is decreased by half. Now in case of O2, you know O2 has bond order 2. For O2 positive, which one is the highest occupied molecule? Pi star 2px and pi star 2py. So we remove electron from antibonding. So bond order is increased by half. For O2 negative, we add electron in antibonding. So bond order is decreased by half. O2 2 negative, 2 electrons are added in antibonding. So bond order is decreased by 1. So this is the bond order. Order of O2 positive is maximum, then O2 negative and then O2 2 negative. That's all for the day. Thank you very much.